We now begin our discussion on Chapter 20 with a deeper dive into thermodynamics. In Chapter 6 in General Chemistry 1, we looked at enthalpy, internal energy, other state functions, and heat and work. Now we're going to look at some other thermodynamic functions, specifically entropy, free energy, and we'll look at their relationship to the equilibrium constant for a reaction. In our first video, we're going to focus on entropy, looking at the second law of thermodynamics, calculating entropy changes in reactions, and looking at the properties of entropy in general. And then in our next video, we'll look at free energy, equilibrium constants, and the energy that we can derive from chemical reactions. As we begin a discussion of entropy, we need to address the concept of spontaneous change. A spontaneous reaction would be one, for example, like the reaction of hydrochloric acid with sodium hydroxide. If we mix these together, a reaction spontaneously occurs, producing water, sodium chloride dissolved in the water, and some excess heat. In general, a spontaneous change is one that occurs without continuously inputting energy into the system from the outside. Chemical processes often require energy, that is, the activation energy that's necessary to initiate a reaction, but once a spontaneous process has begun, no further input of energy is needed. For a non-spontaneous change, we see a reaction or the change only occurs if the surroundings continuously supply energy to the system. If a change is spontaneous in one direction, it is non-spontaneous in the reverse direction. We learned the first law of thermodynamics earlier. We know that energy is conserved. It is not created or destroyed, but it is transferred in the form of heat and work. And we have an equation that expresses this. Delta E is Q plus W, which you investigated in the first semester. And as far as we've been able to observe, the total energy of the universe is a constant, so that the change in energy of a system is always counterbalanced by the change in energy of the surroundings, such that their net is zero. The law of conservation energy applies to all changes and does not allow us to predict the direction of a spontaneous change. What does that mean to us? Well, we know enthalpy can be positive or negative in a chemical reaction. So we can have spontaneous reactions that are both exothermic or endothermic. So we have a number of exothermic processes that we know are spontaneous. At low temperature, a substance will freeze, or a vapor will condense, or a vapor can deposit as a solid at low temperatures spontaneously. Combustion reactions, once initiated, continue spontaneously. Oxidation of most metals is spontaneous. And this is just a small listing of many exothermic spontaneous reactions that we have. There are also examples of spontaneous endothermic processes. So, if we are melting or vaporizing a substance at high temperature, we can see that that occurs spontaneously. And if we take most soluble salts and dissolve them in water, that also is an endothermic process. You notice that when salts dissolved in water cool the system. So what this tells us is we can calculate what delta H is. It can be positive or negative, but that by itself doesn't predict the direction in which spontaneous change will occur. So here's an example of an endothermic reaction that's spontaneous. If we take barium hydroxide octahydrate and react it with ammonium nitrate, we have an acid-base reaction where the base barium hydroxide reacts with the acidic ammonium ion, and the reaction overall is endothermic by 62.3 kilojoules for the reaction as written. The reaction is so endothermic that if you carry out the reaction on a wet board, the board will freeze to the beaker because of all the energy absorption by the reaction. This takes us towards a concept of what actually drives spontaneous endothermic processes. A spontaneous endothermic process results in an increase in the freedom of motion of the system. We're going to see in general that any spontaneous process will result in an increase in the freedom of motion of the universe. But for an endothermic process, we find out that we have to go from less freedom of particle motion to one where we have more freedom of motion. That would mean that we would have localized energy of motion in the reactants, and our products would have dispersed energy of motion. So for our phase changes, solid to liquid to gas, which are endothermic, we see that we're dispersing our particles with respect to their motion. Dissolving salts, likewise, if we have a crystalline solid and a liquid and produce ions that can freely move in a solution, again, we see that we have more freedom of particle motion. A change in the freedom of motion of particles in a system turns out to be a key factor in determining the direction of a spontaneous process. It's not the only one, but it turns out to be very important. And so this leads us to the concept of microstates. So back in chapter 7, we learned about atoms and that they only have certain energy levels that are available to them, the specific quantized electronic states. It turns out that likewise, when we have a large system of particles, that will also have only specific total allowed energy states. And one of these states is what we will call a microstate. So at any instant, the total energy of the system is dispersed in one microstate. Under a given set of conditions, each microstate has the same total energy as any other. Each microstate is therefore equally likely. The larger the number of possible microstates, the larger the number of ways in which a system can disperse its energy. And this leads us to the concept of entropy. We're going to take a molecular view on entropy. Though entropy was originally viewed in a much broader sense and really a macroscopic sense, we now know that the number of microstates, and we're going to designate the number of microstates as W. So if there are 3 microstates, W would be 3. The number of microstates in a system turns out to be related to a concept or a function called entropy. We designate entropy with the letter S. And S is equal to K times natural log of the number of microstates in the system. So a system that has fewer microstates has lower entropy. A system that has more available microstates would have higher entropy. This is how the concept of randomness sometimes is thrown into the concept of entropy. If we have more microstates, we have more ways in which a system can exist. So we'll have a higher probability. All spontaneous endothermic processes have a value of plus delta S, and we find out that plus delta S in general for the universe is what we see. Entropy, when we go back to and look at this, is a state function, just like enthalpy, just like internal energy, just like volume, pressure, temperature, and number of moles. Entropy is also a state function, which makes it very important. Turns out that it's independent of the path that you take between the final and the initial states. Therefore, the delta S for a system will be its final entropy minus its initial entropy. And the value for K is what we call Boltzmann's constant. And Boltzmann's constant turns out to be equal to the gas constant divided by Avogadro's number. Here you see Boltzmann's headstone, and you can see that S equals K log W is carved into it. It's a very important equation. It turns out to have a huge number of applications. So let's look at some examples of this. Let's look at the right. We have a gas that's contained in the left-hand chamber, and the valve between the two chambers is closed, and that's state A. When we open up the valve, what happens? The gas rushes from one side to the evacuated side, such that the two pressures on each side become equal. So if we start off with 1 mole on one side, we end up with a half a mole on each side. This is a spontaneous process. Gas spontaneously expands to fill both flasks. Why does this occur? Well, increasing the volume increases the number of translational energy levels the particles can occupy. So, the number of microstates and entropy correspondingly increases. We can look at this with a simple energy level diagram. On the left-hand side, we have a series of microstates that are available. And we open up the stopcock, it turns out that we have more microstates available. So in a given energy range, you can see that we have more states available on the right-hand side. Therefore, we have more ways the system can exist. Opening the stopcock increases the number of possible energy levels that are available, and they're also closer together on average. And so we have more ways that we can distribute the particles. We can also do a simple probability measurement on this, or probability statement. So on the lower right-hand corner, we have 3 examples. We have 3 cases where the gas is closed. In the first case, we have 1 atom, and it's on the left-hand side. When we open the stopcock, it moves to the right, and you can see that A can be either in the left-hand side beaker or the right-hand side beaker. When we go down to the next state, we have 2 atoms, A and B. If we open the stopcock, we can have A and B on the left, A on the left, B on the right, B on the right, A on the left, or both A and B on the right-hand side. So now we have 4 different ways the system can exist. If we do this with 3 atoms, and you can walk through all the iterations, there are now 8 ways the system can exist. So what this shows us is when the stopcock opens, the number of microstates is 2 to the n power, where n equals the number of particles. So when we go from 1 flask to now 2 available flasks, that's where the factor of 2 comes in. We have twice as many states that are twice as many locations that are available, and then 2 to the n power gives us the number of ways, or the number of microstates, where we can distribute our particles for n particles. So for a reversible process, we find out that the delta S is equal to Q reversible over T. What is a reversible process? Well, it's really mostly a theoretical process. We can approximate it in some experiments, but in general, a reversible process is one that occurs in a series of infinitesimally small increments such that the system remains at equilibrium, and the direction of change can be reversed by simply reversing that infinitesimal change in condition on the system. So that is a reversible process. And we can approximate this in certain experiments. So here's an example where we have a sample of neon gas, and it's contained in a 1-liter vessel. Here you can see the lower half of the vessel in the lower right-hand corner contains our neon gas, and we create pressure in this. It's a piston, and the pressure is created by a beaker filled with sand that sits on top of the piston. If we remove 1 grain of sand, which would be effectively an infinitesimal decrease in the pressure, the gas will expand a very small amount. Therefore, the gas is doing work on the surroundings, and it will absorb a tiny increment of heat from the heat reservoir, the surroundings. So this simulates a reversible process, and then if we put the grain of sand back onto the beaker, we see that we can reverse what we just did. In general, for an irreversible process, or for processes that may be reversible or irreversible, delta S for the system is greater than or equal to Q divided by T. If it's irreversible, it's greater than Q over T. If it's reversible, it's equal to Q reversible over T. This leads us to the second law of thermodynamics. Now, the sign of delta S system by itself doesn't predict the direction of a spontaneous reaction, but if we consider both the system and the surroundings, we find that all real processes occur spontaneously in the direction that increases the entropy of the universe. Thus, for a process to be spontaneous, a decrease in the entropy of the system must be offset by a larger increase in the entropy of the surroundings, such that delta S for the universe is greater than 0. It's a positive value for a spontaneous process. The total energy of the universe remains constant, which we discussed earlier, and oftentimes we'll write the enthalpy down as approximating the internal energy. We find out that for enthalpy, there is no 0 point. We discussed this back in chapter 6. Whenever we measure enthalpies, we always measure enthalpy changes, the delta H values, not the absolute values. This is where we came up with the standard that the enthalpy for an element in its standard state is set to be 0. So we set that as our starting point, and then we make measurements compared to that. Now, as we're going to see in a moment, entropy is a little bit different. The total entropy of the universe increases in all spontaneous processes. And we find out that for entropy, there is a 0 point, and we can determine the entropy of a system absolutely. This leads us to what's called the third law of thermodynamics. A perfect crystal has an entropy equal to 0 at 0 Kelvin. A perfect crystal is one that has no defects. It has no dislocations in the crystal, it has no impurities. So, to the extent that we can make an extremely high purity crystal, we can measure the entropy absolutely for that system. So at 0 Kelvin, the particles have their minimum energy. Since they're all in their lowest energy state, there is only one microstate that's available. And of course, now W being equal to 1, the log of 1 is 0. So the entropy for a perfect defectless crystal at 0 Kelvin is 0. To find S for a substance at a given temperature, we cool it as close as possible to 0 Kelvin, and then we heat it in small increments, effectively reversible increments, measuring Q reversible and the temperature, and then calculating delta S for each increment. Then, if we take this up to some higher temperature, the sum of all these delta S values will give us the absolute entropy at the temperature of interest. So we can measure our absolute values for entropies, unlike enthalpies where we cannot measure their absolute values. S0 is the standard molar entropy of a substance. It's measured for a substance in its standard state, and we use units joule per mole Kelvin, as those are the SI units, at 298 Kelvin. The conventions for defining this thermodynamic standard state, your textbook erroneously puts in 1 atmosphere. We would actually use 1 bar, which is 100 kilopascals, which is the SI standard unit, 1 molar for solutions, and the pure substance in its most stable form for solids and for liquids. Here are some selected entropy values at 298 Kelvin. And of course, you wouldn't need to memorize these. You'll always have standard entropy tables available to you. But let's look at this and see if there's any interesting trends. So you'll notice when we have a liquid and a gas, like for bromine, the gaseous state always has a higher standard entropy, which would make sense because the atoms have more freedom of motion. There are more microstates available. And then if we take something like carbon monoxide versus carbon dioxide, both as gases, we see that the larger molecule, the more complex molecule, has a higher entropy. Then when we take a gas and we dissolve it in water, like carbon dioxide gaseous versus carbon dioxide aqueous, we see that the gas has a higher entropy relative to the dissolved gas in an aqueous solution. So we see that as we go from solid to liquid to gas, the entropy increases, and as we go from smaller molecules to larger molecules, the entropy increases as well. The factors that affect entropy are shown here, some of them. Entropy is a function of temperature. And we find out that standard entropy always increases as the temperature increases. Our entropy always goes up as the temperature of the system goes up. Entropy depends on the physical state of the system, so our standard entropy will increase going from solid to liquid to gas. Formation of a solution affects entropy. In general, crystals that dissolve in solution have an increase in entropy. Gases that dissolve in solution have a decrease in entropy. And we see that entropy is related to atomic size and molecular complexity. Here are computer simulations looking at a crystal, and we see the potential motions, the random walks that atoms take at lower temperature on the left-hand side and at higher temperature on the right-hand side. You can see on the right-hand side, the atoms undergo much larger excursions and they have a much wider range of available positions at that temperature. So adding heat increases temperature, increases the total energy, the particles have greater freedom of motion, and therefore their energy is more dispersed so that the entropy, S, increases. Here's a plot of the fraction of particles as a function of the kinetic energy, similar to a Maxwell-Boltzmann distribution we saw for gases earlier. And as we heat a system and take it to higher temperature, the system will generally shift to the right side and become broader. As we go to a higher temperature, we have more states that are available. Therefore, we have higher entropy. So at any given temperature, there's a range of occupied energy levels and a certain number of microstates, and adding heat increases that total energy, which is the area under the curve, so that the range of occupied energy levels becomes greater, as does the number of microstates. Now we can visualize this going back to what we saw earlier with our microstate diagram. Here we have a system on the left-hand side, which is at lower temperature, and we have 4 available microstates. If we heat the system up, the microstates stay in the same locations. Their energies stay the same. We're not changing the system itself, but now we're increasing the available energy. There are more states available that the system can occupy. So we have a higher entropy. So here we've seen that for this particular system of 21 particles. This is a plot of the measured entropy as a function of temperature for a gas going from the solid phase to the liquid phase to the gas phase. If you turn this on its side, it actually looks kind of like the heating curves and the cooling curves that we looked at back in chapter 12. So now we see the entropy increases continuously in the solid until we reach the melting point. At the melting point, the entropy continues to rise up while the temperature remains constant. Then as the temperature increases, once we have the liquid state, the entropy goes up with temperature until we reach the boiling point where the entropy increases while the temperature remains constant. And finally, the entropy of the gas will continuously increase as the temperature goes up. When we dissolve a salt in water or in an appropriate solvent, we see that the entropy is greater than that of the solid and the water separately. The crystal now has, with fixed atom positions, is dissolved, and the atoms now have much larger freedom of motion. though this is affected by the entropy of the water as it organizes around each ion that's dissolved in solution. When we have something like methanol, a non-electrolyte, which is a hydrogen bonding molecule dissolving in water, we see a small increase in entropy. So here we take ethanol, C2H5OH, dissolving it in water, and we have a solution of water and ethanol. This is accompanied by a small increase in entropy because there are a broader variety of ways in which the two substances can exist, or the number of microstates that can exist for the mixture. For gases dissolving in liquid, the entropy of the gas is already quite high, so when it dissolves in solution, its motions are more restricted, so there are fewer microstates available. The entropy decreases. We also see that entropy is affected by the atomic size. How does this go? Well, in general, the standard entropy for larger atoms is higher than that for smaller atoms. And we already saw earlier that larger molecules or more complex molecules have higher entropies than smaller or less complex molecules. And here we see the group 1 table for the group 1 metals, lithium down to cesium. Of course, these are increasing in size, and their standard molar entropy is increasing continuously. Then we can take the group 17 hydrides, hydrogen fluoride down to hydrogen iodide, and again, the standard molar entropy increases. For allotropes of an element, the standard entropy is higher for the form that allows the atoms more freedom of motion. We can compare graphite with diamond. We know that diamond, carbon is in a tetrahedral arrangement, and the atoms are fixed in position. Of course, diamond's actually quite a hard substance. The atoms don't move very much. And we can compare that with graphite, which has 6-membered carbon rings in sheets looking like chicken wire, and these sheets are stuck together, but they slide against one another, which is why graphite is used as a lubricant. And you can see that graphite then would have a correspondingly higher molar entropy because it has a larger freedom of motion. And in our table here, we see that entropy increases as chemical complexity increases, going from sodium chloride to aluminum chloride, and going from nitric oxide to dinitrogen tetroxide. We can calculate the standard entropy of a reaction simply by summing the entropies of the products and subtracting off the entropies of the reactants. This looks like an equation that's very similar to what we saw for enthalpies. Turns out entropies and enthalpies are handled the same way mathematically in this type of scenario. In general, it turns out there are many cases where we can predict the sign of delta S for a reaction. In general, if we have a change in the number of moles of gas, that allows us to predict delta S. Delta S is positive if we produce a gas as a product. So here we start off with 1 mole of gas of hydrogen, 1 mole of iodine solid. We produce 2 moles of hydrogen iodide gas. There's been an increase in the number of gas molecules, and delta S is positive. On the opposite end, delta S is negative if the moles of gas decreases, like in the Haber-Bosch process. Nitrogen reacts with 3 moles of hydrogen gas to produce 2 moles of ammonia gas. So we go from 4 moles of gas to 2. There's an entropy increase. An entropy decrease. There's an entropy decrease in this case because we've decreased the number of molecules. And finally, delta S for the reaction is positive if we can look at a structure and it seems to form one that is less restricted. So here, for example, we have cyclopropane, which is a restricted structure. This can open up into propene, and propene, being a linear structure, can move more readily. So delta S in this case is positive. decreasing entropy of the system must be outweighed by increased entropy of the surroundings if a process is to be spontaneous. The surroundings function as a heat source or a heat sink, so the enthalpy can move either way. For an exothermic process, the surroundings absorb heat released by the system, and so the entropy of the surroundings will increase. So Q for our system is negative, Q for our surroundings is positive, and delta S for our surroundings is positive. In an endothermic process, the surroundings provide the heat that is absorbed by the system, and so the entropy of the surroundings decreases. Since the entropy is a function of temperature, the change in the entropy of the surroundings is also affected by the temperature at which the heat is transferred. For many reactions, the heat for the system is equal to minus the heat of the surroundings. So the heat is transferred specifically for the reaction is the same regardless of the temperature of the surroundings. The impact on the surroundings is larger when the surroundings are at lower temperature because there's a greater relative change in delta S. So delta S for the surroundings is equal to minus Q for the system divided by T for a reversible process. And just recalling that at constant pressure, Q is equal to delta H. So this is something that is worth noting. Delta S for the surroundings is equal to minus delta H for the system over T. For any process that's approaching equilibrium, that is, it's away from equilibrium and moving towards it, delta S for the universe has to be greater than 0. That is what a spontaneous process is. Something that is away from equilibrium and is moving towards it. And so our delta S has to be positive. At equilibrium, then, there is no further net change. We're finished. There's no net change on the system. And delta S for the system is balanced by a delta S for the surroundings, such that delta S for the universe is now 0. When the system reaches equilibrium, neither the forward nor the reverse reaction is spontaneous. We're now at equilibrium, and there is no net reaction in either direction. We can look at this step by step for exothermic and endothermic processes. For an exothermic reaction, where delta S for the system is positive, and the size of delta S for the surroundings is not important now because delta S surroundings for an exothermic process is always going to be greater than 0. So these reactions will always be spontaneous. Delta S for the system, if that is positive, for an exothermic process, delta S for the surroundings is positive, therefore delta S for the universe is positive. If we have an exothermic process for which the entropy change for the system is less than 0, then the entropy change for the surroundings has to be larger than delta S for the system for the reaction to be spontaneous. So delta S for the system plus delta S for the surroundings equals delta S plus delta S for the universe, which must be positive if it's to be a spontaneous process. For an endothermic reaction in which delta S for the system is greater than 0, delta S for the surroundings has to be smaller than delta S for the system for the reaction to be positive. Delta S for the surroundings is always less than 0 for endothermic reactions because heat is leaving the system. That ends this video. We'll continue on in our next video looking at free energy and equilibrium constants.